In the second part of chapter 23, we're going to talk about lenses. In the lens world, there's basically three types of lenses. There's the flat lens, which really isn't a lens because it doesn't converge light or have an image formed other than just looking through it. So a piece of glass in a window is a plain, I guess you could call it a lens, but really when we're talking about lenses, we're talking about something that can bend light. And that is either going to be a converging lens. So a converging lens looks like this, that when you put something behind it, it magnifies it. And so this is a converging lens. All converging lenses are thicker in the center than they are at the edges. So this is a biconvex lens that is it's convex on both sides, so biconvex. And this is a plano convex lens that it has one convex side and one flat side. And what matters to make it a converging lens is that they're both thicker in the middle. It doesn't matter what side I turn it, it will have the same magnifying properties. Either way we turn it, even though both sides are different, because all lenses have two focal lengths. So if we look at this one, I flip it over, it has the same focal length power. And then there are diverging lenses, which are acting exactly the opposite. They diverge the light instead of converge it. So it looks basically the same as my biconvex lens, except it makes things smaller. So you can see that it's thinner in the middle than it is on the edges. And so it's basically the mirror image of the biconcave lens. This is a biconcave lens, and this is a biconvex lens. And you can see that they're very different, that the biconvex lens will magnify, and where the biconcave will diminish the image. So this is the biconcave, and you can see my head is smaller. Or if I switch, you can't even like see my head because it's so magnified in this. Or if you look at the window, if you look at the calendar behind me, the biconcave lens will make it a lot smaller, whereas the biconvex lens makes it really huge. So lenses, so basically two different types. Converging are the ones that are thicker in the middle. Diverging are the ones that are thinner in the middle. And we'll get into eyes later, but my eyeglasses are diverging lenses to correct nearsightedness, but that's for another chapter. Just like in mirrors, lenses can have spherical aberration due to the shape, and this is where the focal points don't align when we're looking at regions coming from far parts and near parts of the lens. So along the center line, we have one focal line, and then far away we have another focal point. So most mirrors and lenses, to correct for this, have a slightly different shape. They're more parabolic, but then that makes the math more challenging. So for this class, we're just going to stick with spherical mirrors and lenses. And then another property that's unique just to lenses is chromatic aberration. As light gets refracted through the lens, we noticed in the last chapter that different wavelengths of light can refract differently. So that means that the colors will have possibly different focal points, and so we'll get some color separation. And as we go into the chapter where we're looking at cameras and different optical devices, we'll see some of the artifacts of some of these aberrations can cause. So what is this focal length of a lens? Well, every lens has two focal lengths, one on either side, because it really doesn't matter which side you use. So there's a focal length on either side if we're talking about converging or diverging lenses. So the focal point is the distance where if we have light coming in from infinity or very long ways away, then that's where the light will be focused. This is basically the same as the definition for mirrors. So, and again, they have two focal points. A thin lens is what we're going to talk about in this chapter, what we call thin lenses. And thin lenses is one where the distance between the surfaces of the lenses is negligible. So, okay. So finding the focal length for a converging lens. Well, the easiest way to do it is probably just with an experiment. we have parallel rays of light coming in, and where they converge is the focal point. It doesn't matter if we're going right to left or left to right. If you flip the lens over, it will have the same focal point. So a diverging lens is a little bit more challenging because we can't actually see the focal point. What we're going to do is trace these rays backwards, and where they would have converged is what we're going to call the focal point. So these are imaginary lines, basically because it creates a virtual image on the other side of the lens. So the lens equations should look familiar. They're exactly the same as the ones we used for the mirror equations, and we don't have to change the signs or anything because the definitions of the signs we're going to use is slightly different for these versus what we did for mirrors. So a converging lens will have a positive focal length, and a diverging lens will have a negative focal length. So a lens that looks like this will have a positive, and a lens that looks like this will have a negative focal length, which actually is the same for mirrors, that a converging mirror, it will have a positive focal length, and a diverging mirror will have a negative focal length. So this brings us to the sign conventions for lenses, which looks pretty similar to what we did for mirrors, except these signs are switched. The image locations are switched on signs, and the radii are switched on signs. So where the light originates from is typically the front, and we put the object on the front. So we switch colors. So this is where my object is, somewhere in the front. And then the back of the lens is the other side of the lens. So generally the front is defined by where we put our object, and the back is the other side. So this means that when I have an image on the back, it's actually going to have a positive, and this will basically hold our signs true that any image formed over here is going to be a real image because that's where the rays actually converge. Just like for a mirror, we said a mirror had a real image. If I have an object over here and the rays bounce off and form an image over here, we get a real image on this side of the mirror, and it's going to be inverted. We're going to get the same thing with a lens, that the real image will have a positive sign, but this time be on the back side of the lens. However, for a diverging lens, diverging lenses, just like diverging mirrors, can only produce virtual images. So this is the front, and this is the back. So if I put my object here, say an arrow, and then what I'm going to see, if I look through the lens at the arrow, is basically an arrow that appears to be smaller. So we're going to, if the image is on the same side as the object, then we're going to get a negative image position, image location, and that is going to correspond with a virtual image. So the signs will end up meaning the same thing whether they're virtual or real, but you'll notice that the directions flip. So for mirrors, everything on the front was always positive. For a lens, an object on the front is positive. The image on the back will be positive. Then, how do we figure out the focal length? I think I have you using this in your homework exactly once, but this is called the lens maker equation. And so we can find the focal length based on the index of refraction and the radii of the material. So if you wear glasses or have gotten glasses, you'll notice that as your prescription increases, they change the radius of the glasses so that we get them thicker. And we can pick from different materials which have different indices of refraction in order to get a thinner lens as well. So again, this is called the lens maker's equation. All right, now we're going to look at using these equations in this daisy problem. So I'm taking a picture of a daisy, so I need that to show up on the film. We have a 12 centimeter daisy, so that is my object height. It says it's 90 centimeters from the camera lens, so that's P, my object distance, and the focal length of the lens is 120 millimeters. but I want to work in one set of units. I'm going to say f is equal to 12 centimeters, so I don't have to do any more unit conversions. Then we want to find the distance between the lens and the film. The film is where I need my image to be in order to record it, so this is another way of saying my image distance. So we want to find Q. And to do that, I'm going to use my lens equation because I have P and I have F, and I want to find Q. So 1 over Q is equal to 1 over F minus 1 over P. So that means I have 1 over 12 centimeters minus 1 over 90 centimeters. And it's fun to work with fractions, so we want to find the lowest common denominator. Now you could just put those numbers in a calculator and do this in decimal form, but it's more fun with fractions, right? So don't forget to flip it over at the end. Q is equal to 180 over 13, or that gives me plus 13.8 centimeters. So the plus sign indicates that we have a real image. And if I want to draw a little diagram of my system, I have my daisy here. And we get a real image on this side that is upside down. And it'll end up being closer, so it's going to end up being diminished. But we do know that that is real. Then we can use our magnification equation to figure out our image height. What's the height of the image of the daisy? H prime. So H prime is equal to negative Q over P times H. So that gives us negative 13.8 centimeters over 90 centimeters times my original height is 1.2 centimeters. And that means it's negative 0.184 centimeters. This sign means it's inverted. And the number, since the magnification, since our final height is less than the original, so we probably could have guessed that the magnification is less than 1, this means that my image is diminished, which is a good thing for a camera, that we can make something, we could take a picture of something big and shrink it down to fit on the film. There's all those numbers again. Okay, time for you to give it a try. What is the magnification of a diverging lens? So now, since it's a diverging lens, we know the focal length is negative. If the object is located 35 millimeters from the center of the lens. So go ahead and work on finding M. Okay, hopefully you had a chance to do that. In order to find M, we're not asked for the image height or anything, but we do need to find Q in order to find M. We're given P is 35 centimeters, so we need to find Q. Find Q from this equation, 1 over Q is equal to 1 over F minus 1 over P. So 1 over negative 20 centimeters. Don't forget the negative sign, very important. This is where I usually mess up. And I'm just going to do this in decimal form. So I get negative 12.7 centimeters, which sounds reasonable. And the negative sign here indicates that my image is virtual, which we should expect on a diverging lens, because diverging lenses can only make virtual images. So the magnification is negative Q over P is negative, so I get two negatives, a negative here and a negative up here, 12.7 centimeters. And 35 centimeters gives us plus 0.36 as the magnification. The positive sign indicates that we're up, right? And this number is less than 1, so that means we're going to be diminished. We're going to be smaller. So there's all those numbers again.